Welcome back friends to another session of fluid mechanics and rate processes. In the last session we looked at some of the potential flow solutions, very simple ones, and we also looked at the fact that because these flows are linear, they can actually be superposed to give more complicated flows. So we are going to look at some of those flows today by superposing the building blocks. So first we would like to review what are some of the simple flows that we saw in the last class. So we had a uniform flow, then we looked at a source or a sink, and then we also looked at a free vortex. So let's see what the stream function and the velocity potential for these flows were. A uniform flow is essentially flow is exactly the same everywhere, and the streamlines are inclined at an angle of theta to the x axis. So for such a flow, we said the velocity potential is simply given as v infinity, if v infinity is the speed, cosine theta times x plus v infinity sine theta times y. And the stream function psi for the same flow can be written as v infinity cosine theta y minus v infinity sine theta x. Okay. Next we come to the source. So a source flow was described as, if I have it at the origin, these are the streamlines, so that's a source, and the strength was Q. Q represents the volume flow rate that comes out of through this origin. So this is a source located at origin, so I mark it with O. And for this we were able to show that phi is Q by 2 pi natural log of R, and for the same the stream function was Q by 2 pi theta. Notice the streamlines are psi equal to constant lines, and they in fact imply theta is constant, which means they are lines which are radially outward. If I wanted to do a sink, then all I have to do is that Q has to be less than 0. So then the direction of the streamlines would be reversed, and instead of the flow going radially outward, for a sink the flow would come radially inward. Okay, next we come to the free vortex. So here if I look at the streamlines, then we talked of them being as circles. And this was the sense of gamma. Gamma is the circulation, and we were able to show that for this flow the velocity potential is given as gamma by 2 pi theta, and similarly the stream function is essentially minus gamma by 2 pi natural log of R. So in this case you can see for the streamlines the stream function equal to constant would give us R equal to constant, and those would essentially be circles. Be careful about the sign. These are streamlines that go around in a counterclockwise direction. So that's the sense of gamma. On the other hand, if gamma is less than 0, so if I take gamma less than 0, then I just have to account for the sign in psi and phi, and these would imply that I have a clockwise rotating vortex. Okay. So these are the three building blocks that we have seen, and now because we are allowed superposition, because each one of them is a solution to the governing equation, and let me remind you what the equation is. It is del square phi is 0 and del square psi is 0. So the Laplace equation. And because each of these flows is a solution to those equations, their linear combination is also a solution. So now we are going to try superposition. So some simple potential flows via superposition. The first flow that I wish to talk about is the Rankine half body. This is a flow that is obtained by superposition of a uniform flow and source. So imagine there is a source placed at the origin. So let me put the axis. This is the x axis. This is the y axis. And I could put a source here. And I have a uniform flow that comes in from the left. So far away from the origin, this flow has a speed of u and it is aligned with the x axis. Okay? So the total potential that I would see from this flow would be simply the potential from the uniform flow, which is u times x, and that I can obtain simply from here. Okay, so I have replaced v infinity with u, and because theta is 0, so cosine theta is 1, this term vanishes and I just have x. So u times x, and to this I add the potential due to the source, and right here I have the potential due to source, q times q divided by 2 pi times natural log of r. Okay, so it's as simple as that. So if I actually take that potential, it represents whatever is going to be the resultant of these two entities. Similarly, I could talk about the stream function. The stream function also can be obtained simply by superposition, and this is uy for the uniform flow, and I have q by 2 pi theta for the source. Okay. Next, what I can do is try to obtain Vx and Vy. These are the x and y components of velocity. As you know, Vx is actually del phi del x. In fact, I could also obtain it from the stream function, and that would be simply del psi del y. So I can use either the phi equation or the psi equation, it's up to me. Both will give me the same answer. So del phi del x, as you can see, would be simply u plus q by 2 pi x divided by x square plus y square. Similarly, Vy is given as del phi by del y, or I could do minus del psi del x, and that would be simply minus q by 2 pi y divided by x square plus y square. Okay. So, I am now able to see that for this kind of a flow, a uniform flow coming into a source, that is the velocity field that I generate. And in fact, you can find flows very similar to this in nature, and we will talk about it after we have seen the streamlines for this flow. The streamlines are given as psi equal to constant. So, if I take this function and I simply put psi equal to constant and I change the value of the constant, I would get different streamlines. Let me sketch them for you. So, this is my x axis and this is my y axis. This is where my source is. And what we will find is, so I will draw the streamlines for you and then explain you. This is one streamline that we would get, and there would be others which would look like this. So, it would be symmetric about the x axis, okay. These are the streamlines I would get over here. This would go like this would go like this. Maybe I will draw this with a red line, and then outside this body I would get streamlines like this. It is very easy to do this on a computer. All you need to do is take this function, put it in MATLAB, and then plot it for different values of the constant. So, you take psi equal to a constant 0, plot this function, then you take another value and another value, and you would get different streamlines. But this is what you would see. Okay, this is the origin O, and maybe I will call this point as A. All right. If you remember, the definition of a streamline is that the tangent to a streamline gives us the direction of the velocity vector. So, it automatically implies that there are no flow can cross a streamline. Okay. So, that means if I take any of these streamlines, there is no flow across it. And because we are dealing with an inviscid flow, frictionless, we could actually replace any streamline by the surface of a solid body. So, this observation I will write down for you. So, we can replace any streamline with the surface of a solid body. This is very interesting. So, what is being said is that in principle, if I wanted to, I could replace this streamline, for example, with a solid body, and then I would actually get what is the flow, the potential flow if I had a body of this shape. There would be flow external to it, and the internal one is actually a body, and I don't have to worry about that flow. Similarly, I could actually replace the red line, this surface that I have traced, with a body, and in fact that's called the Rankine half body. So let's look at some of the features of this flow. So the first thing we want to do is talk about this point A. Okay. As you can intuitively feel, there is a source here which is squirting out fluid in all directions. Okay. It is an isotropic source, so it squirts out fluid with the same radial speed in all directions. But then there is another fluid coming in with a uniform speed, uppercase U, and somewhere this fluid would come to rest, okay, at this point, because there is a radially outward flow and this one is trying to push it towards the origin. So A is known as the stagnation point. So A corresponds to stagnation point. What that means is that at the stagnation point, the velocity at x equal to xa is a 0 vector. So what it implies is that both components of velocity will be 0. So let's work that out. So if I want v at a, the x component to be 0, and I want v a y component to be 0. So first let's take v a x equal to 0. So that's this part. Okay. That clearly implies that I would get so this implies that u plus q by 2 pi x a divided by x a square plus y a square, this is 0. Now if I want v y to be 0, the y component of velocity to be 0, then I have to take this equation, and this would simply give me that y a is 0. Okay, y a is 0, that is what I would get from this. So if I plug that in this equation here, then I would simply get that x a is simply going to be minus q by 2 pi u. So that is the location of the stagnation point, which lies along the x axis. It is very clear that if I had the source of a high strength, then x a would get pushed a little bit more to the left. On the other hand, if I had u of a much larger uniform flow, then that would try to push the stagnation point closer to the origin. So that is the competing effect that q and capital U have on each other. A streamline that passes through the stagnation point is called the stagnation streamline. So let me write that down here. So we are going to define the concept of a stagnation streamline. And that is a streamline that passes through stagnation point. And in fact, that is why I plotted this line in a different color, in the red color. Maybe I will draw it a little bit thicker so that it is visible on your screens. So this is the stagnation streamline. So, the way to find out the equation for stagnation streamline is that first I estimate what is the value of psi at x a y a. So, I can do that very easily. So, psi at x a comma y a, where these are the stagnation points. So, I go to this equation. At the stagnation point y is 0, and therefore, I would get this value to be q by 2, okay, because at the stagnation point my theta is actually pi, right. So, these correspond to theta equal to pi, and if I substitute that, the value of psi is q by 2. So, therefore, if I had to trace my stagnation streamline, so my equation is simply the following. For the stagnation streamline, all I need to do is say that q by 2 is equal to this function, which is u y plus q by 2 pi theta. So, if I draw this function, then I would get the stagnation streamline, and in fact that has been drawn here. So, I just want to spend a little bit of time on this. This point, as you can see, is a very interesting point, because here two streamlines are intersecting, and we have already studied that streamlines cannot intersect. In general, streamlines cannot intersect because the tangent to the streamline tells us the direction of velocity. If they are intersecting, so suppose I have streamlines that intersect, that means at this point I have two directions, a direction A and a direction B. How can a fluid particle or a fluid element have two different flow directions? So, they cannot intersect unless it is a stagnation point. At the stagnation point, the value of the velocity is 0, and a 0 velocity vector does not have a direction. Okay. So, this point is a little bit special, and so is the case with all stagnation points, that the streamlines actually intersect there. In fact, what you will see is that my source was placed here. So, this is the direction of streamline that passes through this. It actually goes to the left, and then this is my stagnation point. The free stream flow comes in again from left to right, and then it goes in this direction. Okay. So, it is a very interesting set of streamlines. You will also know that the flow is symmetric about the x axis. Okay. Of course, it is not the same about y axis. Now, if you notice carefully, this shape here, I could actually replace this with a solid body, right, and I would get flow past this red colored body, and that in some sense looks like the nose of an airfoil of an aircraft wing. So, if I take a close up view of a wing of an aircraft, so this is an airfoil, and if I look at the zoomed in view of this, okay, so you can see that I am talking about the flow very close to an aircraft wing.